Moving on with the applications of parabolas, which is exercise 7F in your book. Now, in this one here, we're starting to look at a trickier example where we need to generate a few equations, swap them out, and then solve, okay, by finding the maximum. Now, this stuff actually lends itself to calculus. If you've ever seen calculus before, you're starting to do what calculus can do here in this example. Okay, so here's our situation. We've got a piece of wire. It measures 100 centimeters in length. Okay, so we've got a 100 centimeter length wire, and it's bent into the shape of a rectangle. And they're saying let x be the width of that rectangle. Now, what's going to help us out here is probably drawing a diagram to start us off. Okay, and this is x here. Okay, now we're not given another dimension, so I'm just going to say that's L. Okay, we're not really sure what that's going to be yet. And yeah, so we've drawn that there. It's just to help us remember what we're trying to do here. Now, for part A, it says use the perimeter to write an expression for the length of this rectangle in terms of x. So we can picture that we're unfolding that piece of wire, right? So you've got this piece, that's a piece of the wire, this piece, and this piece, and it's all folded. And in total, that's going to make 100 centimeters. Okay, so what's the perimeter equation going to look like? Well, you're going x, and there's two of those, right? Plus 2L is equal to 100 centimeters. So that's what the total is going to be. Now, this is going to represent our first equation. Okay, now the reason I'm going to number that is we're going to talk about a few equations here, so it's nice just to number them, keep life easier. Next, write an equation for the area of the rectangle. Now, we can see that this is going to be at the moment x times L. So width times the length. So let's write that in. Area is equal to x times by L, or you can just write XL, and that's our equation 2. Now, we're going to have a look at making an equation here by swapping out some variables. Do you see at the moment, like, it's really hard to sketch an equation that has two variables? We don't really like that. So what we're going to try to do here is use equation 1 to help swap out one of these variables. Okay, now in this case here, we want to get an equation just in terms of x. So do you see that first equation? I can rearrange everything in terms of L, then substitute that into equation 2 to get rid of that L and replace it with x. So let's rearrange that. So I've got 2x plus 2L is equal to 100. 2L is equal to 100 minus 2x, divide every term by 2. And this is going to be my equation 3. Now that I can have that equation L, the length, is equal to 50 minus x, I can substitute wherever I see L with the L in my original equation here, A. So let's do that now. And this is equation 4. You could also express it like this if you so wish. It's just a different way, just expanding it. Now what we've done is we've got an equation for area, but it's only in terms of x. And now we can actually start solving for this thing. Now it says sketch. To sketch, we need to find some key values. Now, this form here is probably of more help because this is in factored form, right? So we can find right away our x-intercepts. So let's use this form here. The x-intercepts are going to be 0, 0, and 50, 0. That means our line of symmetry is going to be in between 0 and 50, so it's going to be 25. So now we're getting somewhere. We've found the line of symmetry, and this is going to be, we're going to plug that in and find out what the turning point is, and hopefully this will be a maximum. So let's plug that in to our original formula. So there we go. We've just found the area for this, and the turning point is going to be at 25,625. Now, what we're going to do is we're going to draw a graph of this, x and a, and this is the width of the rectangle, and this is in centimeters, and this is the area of the rectangle, and this is measured in centimeters squared. So now let's put in our key points. We know that there is a x-intercept at 0, 0, and also 50, 0. We also know there's a turning point halfway around here. Now we need to draw some kind of parabola like that, and let's label what those are. Okay, so the graph, so we've sketched the graph, okay, and then it says use the graph to determine the maximum area that can be formed. So we can say that if x is equal to 25 centimeters, then we have a maximum area of the rectangle of 625 centimeters squared. Now, question F says what will be the dimensions of the rectangle to achieve its maximum area. So we know that x is 25, so we're going to plug in 25 into our L formula equation 3, just here. Okay, so what happens if we plug that in? So dimensions, this is to do with question F, L is equal to 50 minus 25, which is 25. So the dimensions are a 25 by 25 centimeter enclosure. Okay, and so we just work this out here. If this is 25 and this is 25, then we've maximized the area. Now, an interesting rule of thumb, if we want to maximize the area for a rectangular enclosure, it's going to be tending to a square, unless there's some additional restraints that are being put on it. So there we go. We've had a look at this question here. We've sketched it. And yeah, I think that question is probably a little bit tricky, but once you practice a few of these, you get the hang of it. Main strategy, forming a few equations and trying to swap out one of the variables so you only have one variable instead of two, then you can start solving the problem. Now, a really similar question there. Have a crack at that and then we'll go through the answers. So pause the video, have a go at that your turn, and then we'll go through the answers. All right, let's go through the answers now. So circle that. Okay, so you should have just a quick rectangle, x, L, and perimeter equation. Perimeter is 2x plus 2L. In this case, we've got 80 centimeters, so you should have an equation that looks like this. Equation 1. Now let's generate an area equation. So length times x. And now we want to sub in and get rid of that L. We know how to do that already from the previous example. So 2L is equal to 80 minus 2x. And then we're going to go L is equal to 40 minus x. And we're going to sub that in. Equation 3, we're going to sub in into equation 2. So area is equal to 40 minus x times x. Next, we've got our equation. We're going to sketch the graph. So let's find some key features. We've got the x-intercepts at 0, 0 and 40, 0. Therefore, the turning point is going to be at 20. Sub in 20 into our area rule, and we can see it's going to be 20 times 20, which is 400. And now we can start sketching this thing. Okay, x, area of rectangle, and this is going to be centimeters squared, and this is going to be the width, and this is centimeters. Okay, put in our key points. We've got a 0, 0, we've got a 40, 0, and in between we've got a 20. Okay, we've got a graph there. Let's label those. And then let's talk about answering the rest of these questions. So we can see for E, the maximum area is 400 centimeters squared. F, what will be the dimensions? A 20 by 20 should do it. So there we go. Hopefully you got that answer there. This one here, it's tricky at the start, but if you keep practicing, you'll get there. The questions I recommend doing are here. So as always, the more questions you can do for applications of parabolas, the better you go. Yeah, just try to get your hands as many of these as you can until you really feel solid on it. Okay, thanks very much for your time today, and I hope you found this video useful.